See, impulse turbines. Very simple. It is given in a very simple language and all. I will share it in the group. Okay, so please go through them also. But meanwhile, I'll explain what the contents very briefly. Okay. See, impulse turbine, what does it do basically? See, the flowing currents, when you, it's the water under pressure coming through a pipeline, water flowing under pressure in a pipeline, so that will possess definitely kinetic energy and the pressure energy. Okay, because water is inside the pipeline, and the kinetic energy and pressure energy. And if you are making use of the pressure and kinetic energy of water to operate the turbines, to extract mechanical power, if you want to use both kinetic energy and the pressure of water, then such type of category, that is reaction turbine. So at the inlet to the reaction turbine, the water will be possessing both the pressure and kinetic energy. And then such a system, that will be a very closed conduit flow. It is pressure tight casing and all available. So air has no access to the access inside the turbine. It's not open anywhere. Okay. So such open in the sense, through the inlet water is coming, through the outlet water is draft tube and all water is going out. And it's a pressure tight casing, and the flow under pressure. And as the flow proceeds in a reaction turbine, the pressure is pressure goes on decreasing from inlet to the outlet. So important idea you have to keep in mind: in a reaction turbine, the water at the inlet that possesses both kinetic energy and pressure energy. But in an impulse turbine now, see this impulse turbine, it works, as the word rightly implies, it is actually it works under the impulse of water. So the direct action, it's not reaction. So the kinetic energy of the water is fully utilized by the turbine, not pressure energy. The pressure is atmospheric. It's very important thing you have to keep in mind is this: the pressure at which the operation of impulse turbine takes place is atmospheric pressure. It is not high pressure. See, whatever pressure the water flowing through the pipeline or penstock up to the turbine that possesses, the entire energy is converted to kinetic energy by utilizing a nozzle in the case of impulse turbine. So impulse turbine, before striking the vanes fitted on the periphery of a runner, which we call Pelton wheel, and the entire energy, the complete energy associated with water is converted to kinetic energy. How? By using a nozzle. And the pressure, the moment jet comes out, that is a free jet. The moment the jet comes out of the nozzle, that is a free jet. That means the pressure is atmospheric. So throughout the operation of the impulse turbine, the pressure is atmospheric. That is the key point you have to keep in mind. So you can say that the impulse turbines make use of high head of water, and all the pressure energy possessed by water at the turbine inlet is converted to kinetic energy before the water jet is striking the vanes. So the water jet striking the vanes, it will be a free jet, free liquid jet. That means the pressure will be atmospheric. Then what does it possess? It possesses enormous kinetic energy. Okay, so that is impulse turbine. It works under the direct impulse of water. Okay, so the impulse turbines change the velocity of the jet. Jet impinges on the turbine's curved blades, which almost reverse the flow, and as per Newton's second law, the change in momentum exerts, that causes a force on the turbine blades, and the turbine is spinning. The force acts through a distance. Even the force of the force exerted, that point of application is displaced in the direction of the force, work is to be done. Okay, so that the water flow is left with diminished energy, that is outgoing water, the deflected water. And prior to hitting the turbine blades, the water pressure and the entire energy associated, because ultimately the water is stored in the dams, that contains at that stage, when that is stored in high head reservoirs, it possesses enormous potential energy. And then that comes, through the penstock, larger pipes, it comes to the powerhouse where the turbines are installed, and there the potential energy is converted to kinetic energy and pressure energy inside the pipeline. And then we use a nozzle that is fitted at the end of the penstock, that pipe. So therefore, the entire energy, whatever kinetic and pressure, that is all completely converted to kinetic energy alone. So the water comes out of the nozzle, that will possess only kinetic energy, and the pressure will be atmospheric. That's why we say free liquid jet. Okay, and no pressure change occurs at the turbine blades. That is a very important point. And the turbine doesn't require a housing for the operation. See this idea, the impulse type of turbine, since no pressure changes that takes place during the operation of the turbine, and that is atmospheric pressure only, air has access inside also, and the turbine doesn't run full, and it's not at very high, not at pressure, pressure, not a pressurized flow, it is only atmospheric flow operation that takes place at atmospheric pressure. So therefore, only for the danger of splashing water and all, the casing is provided. Otherwise, there is no hydraulic function for the casing. And Newton's second law that describes the transfer of energy for impulse turbine. Newton's second law means what? Whenever there is a rate of change of momentum, an external force is exerted. That's how, so the water jet, when it passes over the blades, what will happen? It undergoes a change in momentum. So because of Newton's second law, so we can say that a force is exerted. Then that force is responsible for the rotation, or the responsible for the torque generation, and consequently the runner will rotate. So impulse turbines are most often used for very high head applications and all. So when you think of state like Kerala and all, when high head water storage or high head dams are available, and if suppose you can have water head to a level of 500 meters water head. So from the powerhouse level where the turbine is installed, the water stored in the dam, that is at a height, a vertical height of 500 meters or so. So we can treat this as a high head turbine. So this 500 is not a level by which you say high head turbine. I'm giving an example only. So any head that is greater than say 200 or 250 meters is rated as high head turbine. 200 meters and above, now usually in a practical sense, we will consider as a high head turbine. See, this is Pelton turbine bucket, so here bucket, or this is called this double split, this hemispherical vanes, or we call it hemispherical buckets. Don't get confused, the word bucket. Hemispherical vanes or buckets. See, it is double hemispherical, double cups. There is a splitter inside. See this? You can see that these are the blades fitted on the periphery of the Pelton wheel. This is Pelton wheel runner, or you can simply say Pelton wheel. So a heavy wheel along the periphery circumference of which these type of blades are mounted. These are double hemispherical cups, double hemispherical vanes called hemispherical buckets. There is a splitter, the jet will be striking here and split, half the portion goes this way and half the portion goes this way. So that's it. And even we have more diagrams to explain this better. For time being, just consider that this is a Pelton turbine runner, and on which you have a number of vanes are fitted on the periphery of the wheel. And this is again another diagram that gives you an idea about a vertical, the runner in a vertical plane and the shaft is horizontal. See, this is a shaft. This is a schematic representation. You have double hemispherical cups, this type of vanes are used, or called buckets, double hemispherical cups and all. And the use of, why do we use double hemispherical cups instead of a single curved vane? And that is again another question, and we have to search answer for all these type of questions. And if you want to draw in exams and all, see this this is again a schematic diagram, but that clearly explains the Pelton turbine runner and the other parts. See, if you want to identify the parts, actually high head water, high pressure, and see, this is the pipeline actually, penstock pipes. See, it's coming from very high head actually, from a height. So it comes inside, and then, so don't be under the impression that it comes from below. So it's actually comes through the penstock, that is, maybe the pipes are below the ground, and then it comes like this. But it is actually coming from high head dams. very high pipes, very large pipes which carry water from the dam to the turbine inlet. Such pipes are called what? Penstocks. So through the penstock pipes, this is coming, water is coming, and that water will be having high pressure and kinetic energy. And then we have a nozzle. See, this is a nozzle actually, and a nozzle, this is a spear arrangement. See, there is a spear here, and this is to control. Normally we call it a needle valve or spear valve. This is to control the flow, to regulate the flow. Turbine discharge regulate flow rate regulate and when this is moving in, this spear this valve, the opening will be nearly closed. So when it is withdrawn, flow rate koodum, flow rate korreyum. So this is a spear or needle valve arrangement used in the nozzle to regulate the flow. So what is the purpose of the nozzle? It is to convert all the energy possessed by water at in the pipeline, in the penstock pipes, to kinetic energy. So to kinetic energy alone. So whatever energy possessed by water, and that is completely converted to kinetic energy in the nozzle. And this spear valve arrangement inside the nozzle, that is for regulating the flow or control the discharge. Okay, it is controlled automatically. There is a governing system. It's not manually operated. You cannot do that because you are talking about very high discharge. Okay, then there is a part which is going in like this also. See, there's a braking jet also. He is not there. So braking jet means to stop the rotation of the runner. See, this braking jet, that is to brake or to bring the turbine runner to a standstill condition. So if you want to stop the turbine from operation, this is a heavy wheel, and even after reducing the flow rate to 0, the turbine wheel keeps on running because of very high inertia. It's a heavy wheel because this is fitted on the periphery of it. So the more weight concentration is towards the periphery. Naturally, the turbine runner has a high moment of inertia, and so once it starts rotating, so that it has the necessary momentum to keep on rotating. So even if the discharge is stopped, the flow rate is stopped, it will not come to rest all of a sudden. But the generator shaft, that is coupled, the generator is coupled with it. So when this comes to a stop, the generator has to be stopped. So therefore, the turbine wheel has to come to a stop. So if you want to stop the turbine within a certain time, within a small interval, you require a braking effect. For that purpose, the braking jet is used. The braking jet that will strike opposite to the driving torque. So this will produce a braking torque. So it impinges. It impinges if the jet is striking here, and it will rotate in the anti-clockwise direction, but braking jet will produce a torque in the clockwise direction. So that means it will act as a braking torque. So the turbine runner rotates in the anti-clockwise direction, and the braking torque is provided in the clockwise direction. So it can be stopped abruptly if you want, in case of requirement. So that's how. So the nozzle with spear valve arrangement to completely convert the kinetic energy, the energy possessed by water completely into kinetic energy. So the moment the water jet comes in, throughout the turbine operation, the pressure will be atmospheric. See, air has access from below. This is open actually. There is a casing also. See, this casing is provided, and casing has no hydraulic function to perform. That it is not used for any type of energy conversion, and this is just for avoiding splashing, to avoid splashing of water, to avoid such dangers. We use it. No hydraulic function. Okay, because the entire pressure, level that prevails during the entire operation from inlet after the nozzle, inlet to the discharging level, the atmospheric pressure prevails. Okay, this is a runner. As I told you, that has buckets, double hemispherical buckets mounted on the periphery. Okay, runner with buckets, the casing, then nozzle with the spear arrangement, valve arrangement, braking jet. Okay, these are all the important parts. So tail raise means, see, tail raise in the sense water level in the dam is called overhead dam, that is head raise, and the water in the water level in the place where water is discharged from the turbine after usage, after extracting energy, and that is called a tail raise. Actually, the distance from the vertical distance from the head raise to tail raise, that will be the gross head available. And now this is a symbolic representation, jet of water striking the splitter. See, splitter, I told you, actually, if this is the runner, the splitter means that is the partition in between the double hemispherical cups. Okay, so the water jet, that comes here. And don't get the impression that, don't be under the impression that this jet is circular, rectangular. It is actually a circular jet, but this is just for the sake of explanation. Okay, so the jet is circular, and this is what is shown over here. It's like a rectangular cross section. It's not rectangular. This is only symbolic representation how it is getting deflected. This is a section of the hemispherical vane, and this we will use later on. We use this one for drawing the velocity triangle. So the vane is shown over here. Okay, and jet is angle of deflection. Normally we say what is that, 180 minus theta. See, that is shown over here. And if it is a perfect hemisphere, the angle of deflection will be 180, and here it will be slightly less. And why it is so, we will explain. Even though hemispherical vanes theoretically provides us the maximum hydraulic efficiency, in actual practice there is always a vane clearance outlet tip vane angle greater than 0 for some practical purpose. And what is that, we will explain later, or else you find out. And the angle of deflection is 180 minus theta. Theta is that inside part. This part is theta. Outside this is 180 minus theta. And when the angle of deflection is 180, that means the vane angle at outside tip is 0. And that means exactly perfect hemisphere. And even in the Pelton turbines, not perfect hemisphere. That's what, for obvious practical reasons, which we'll explain later. And this is the velocity triangle that I will explain later. Okay, because we'll study this in detail. But for time being, this is how the water comes in. But remember, cylindrical jet issued from the nozzle, and it gets deflected both ways. There is a splitter in between. There the water is striking. So the water is divided equally into two halves actually. And angle through which it is deflected, this is the deflection angle. And the inside angle here is the tip angle, the vanelet tip angle, that is represented here by the letter phi. Sits over here. So the velocity triangle, you will understand. This is basically a diagram layout of hydroelectric power station, but this is ideally one suitable for reaction turbines. It's not a high head one. It is shown reaction turbines and all. You know why I am telling this? Because of this turbine shown over here. If this is of this type of cross section, that is, that either it's a Kaplan turbine or a Francis turbine schematically. And in simple turbines or small scale turbines, you can think of shaft which is horizontal and turbine is in vertical plane. But in very huge turbines, this is the configuration in which the turbine is oriented or installed. So we have the turbine here. See, this is the turbine runner. It will rotate here, and this is the shaft. And above the shaft, above the turbine, you have on the same shaft, you have the generator, and that is a powerhouse. And above which, if the generator is above the turbine, definitely that will facilitate the transmission of electricity. Ultimately, you have to convert this water power into electricity, and the turbine converts the water power into mechanical power, and the generator converts that mechanical power into electrical power. And that electricity is fed over the grid lines, showing overhead grid lines shown over here. Okay, so this is the idea, and that discharge from the turbine is going to the rivers and all, that is it. And this is the dam or the reservoir. It's only a schematic diagram, and the penstock, don't be under the impression that the height is very less and all. This is typically what is shown over here is a reaction turbine where the head is low. Head means that height under which it is. So the head of water that is available, so from the reservoir to the tail race where the water is discharged, so that is a head, that is called a head. So this is a simple schematic layout, and you must have seen earlier. This is a laboratory setup of a Francis turbine, and for small turbines the shaft is in horizontal, runner is in vertical position. But for very huge power stations and all, this runner will be in a horizontal plane, and the shaft will be vertical. and that will facilitate the fixing of generator above generator rotor above the turbine and all, and that will be having tremendous advantage, that type of layout practically. So this is a laboratory setup, and you have water is entering through this pipe, and it has a vortex or volute volute casing, and then the water after deflection, see inside, this contains a runner where the vanes are radially mounted. This is a Francis turbine experimental setup in the lab and all. And here it is the water after deflection, after giving away its energy to the rotating runner, it moves out. See, through this to the tail race. Tail race means where the water is discharged after usage. And typically these are all the turbine runners used. So this is, you are familiar with this one already. This is a Pelton turbine runner. You can see the hemispherical, double hemispherical buckets or vanes fixed on the periphery. And you can have, this is a typical Francis turbine runner for small turbines, and 3-bladed only Francis turbine. And this is again for the Francis turbine, and where the runners, see this is a runner, and the blades are radially mounted. See, these are the vanes fitted radially on the runner, Francis turbine runner. This is Kaplan turbine runner. There is a central hub, this resembles like a propeller fan, Kaplan turbine runner. So we will deal with it more as the class progresses. Okay, so the Francis turbine runner, this is typically a Francis turbine runner. See the blades radially mounted. These are this, and it is usually mounted in a vertical plane. The shaft will be vertical, and the runner will be horizontal, shaft will be vertical. Shaft position is vertical, and this is actually an installation of Francis turbine runner in Grand Coulee Dam in the US, and of 750 megawatt, 1 million HP hydroelectric power station. See, the world's largest, that being, that is operated, that is in China, installed in 2009. That is in Three Gorges River, Three Gorges Dam. That has enormous capability, 12,800 megawatt and all. So the Pelton, Francis turbine runners several Francis turbine runners are used. And this is the basic, the skeleton which you can understand from this, the generator here, cutaway sections and all. And you have the turbine runner fixed vertically, and the water will be entering, like this. And these are these wicket gates. What is written here is stationary vanes which will guide water, but it is in reaction turbine, basically reaction turbine runners. So this is an axial flow, Kaplan runner, in fact. So we'll understand when we study this clearly. Axial flow reaction turbine. Radial flow or mixed flow reaction turbine is Francis turbine. And again, another cut section view. Here you have the Francis turbine rotor and the blades. You can see over here. There is a special casing. This is actually called, this one is a spiral casing, a scroll casing, and that is a peculiar hydraulic function. Then throughout when water flows through the casing, what is happening is its pressure energy is converted to kinetic energy. See, as I told you, for the reaction turbine, that is a pressurized tight casing, and water under pressure will be flowing through reaction turbine. But for the Pelton turbine, water will be at atmospheric pressure from the inlet to the turbine after the nozzle to the exit of the turbine. So this is again a schematic representation showing the head and all, gross head and net head producing work. This head is important for us, this height, and all the other losses are shown over here. The penstock, the frictional losses in the penstock and all, frictional HF is represented HF, and the velocity head ultimately we'll see that is also the part of the head that is there. And the turbine, the pressure head is shown over here, just like the hydraulic gradient lines, which you plot in fluid mechanics for the flow passage. Similar to that, the various levels of head that have been, various levels of heads have been indicated over here. And tail race is the place where water is discharged, and the head, the water level in the dam, stored in the dam, that is a head race. And the total head, effective gross head, means the vertical height between the head race and the tail race. See, that is important. And the other, again, schematic cut section views of a Francis turbine. And you have the turbine runner, generator above that. This is the turbine runner, and the scroll casing the casing is cut section in view. So just like two circles shown over here is a part of that cut section if you take the casing. Just like if you cut a tire of an automobile, see like that, the toroidal shape, that will give two circles. Here one will be small and other will be big in this case because it is made in that way. Progressively as the flow occurs, the area of flow has to be reduced to convert the pressure energy into kinetic energy in a reaction turbine. And the conduit or the pipe through which water is discharged in a reaction turbine, that is called draft tube. Okay, so that is also there. And now the axial turbine story and all, we will come to that later in one by one, but just I am giving you an overview of that. These are the type of turbines we will come across. This is a Kaplan turbine runner, and in fact the one which we use in our college lab, that has the similar Kaplan turbine experimental test rig. That turbine has a runner having this type of shape. These are the blades and this is the hub. So axial flow takes place. The flow from here, so from the back along the axis it comes, and after deflection it moves to the front parallel to the axis. That's why it's called axial flow. And axial flow turbine here, this diagram, this is useful for you for drawing schematic diagrams of the Kaplan turbine runner and experimental setup for the examination purpose and all, schematic diagrams and all. Okay, other diagrams, and this is again a Kaplan turbine runner, velocity triangle. We'll talk about that later, and these kind of relations and all we will consider. And governing of turbine, that is actually controlling the flow or regulating the discharge or flow rate through the turbine, that is called governing based on the load requirements. An oil pressure governing system is used in Pelton turbine. This is for the governing of heavy duty turbines called reaction turbines. And recent years there are other type of turbines that also come into picture, again like a reaction turbine, very low head, and this type of turbines called bulb turbine. This is fish friendly. Fish friendly means completely immersed in and it is underwater, and this is typically called a fish friendly turbine. It won't produce any harm to the aquatic animals and all. Okay, so with this I wind up, and then just to keep some ideas in mind, about impulse turbine and reaction turbine, and in full-fledged manner with the velocity triangle we start from the next class onwards. And meanwhile, tomorrow there will be a tutorial session that will be handled by Assistant Professor Nandu, and the topic will be again impact of jet on vanes. Thank you so much.